Okay, first, Victor Miller, who's one of the co-inventors of elliptic curve cryptography, happened to watch the video from class on Wednesday, which is nice, and he sent me an email and he said that I was wrong, that there was no existing English proof that the continued fraction of e is what I claimed it is, namely that thing with a nice pattern. There's a paper from 1970 in the American Math Monthly, and here's the reference, which is all about the continued fraction of e. So everybody who looked before who I had looked at this just missed that. I guess the title should have given it away. Apparently no one decided to search for that title, but there is a nice paper. So I just wanted to add that fix. And I'm going to talk on the whiteboard a bit about the fact that all rational and real numbers can be represented, and I'll give two proofs. So this will be like a purely theoretical discussion. But first, I just want to show you how to work with continued fractions in Sage, and some examples of continued fractions, and then we'll get back to the theory. So there's a command in Sage which takes as input any number, and the command is called continued fraction. So we just type continued fraction, and then question mark. You can see the help about the continued fraction command. So here it is. I'll tell you all about that, but what you do is you give it a number. So like 2014 divided by 786,543. Then you evaluate it, and what it gives you back is a continued fraction. And that's a certain Python class, and you can do various things with it. If you just print it out like that, it shows you the numbers A0, A1, A2, A3, A4, A5. There's another thing you can do. If you do show of this thing, it gives you back the continued fraction written out as a fraction. By the way, if you completely forgot everything up until this very moment in the course, and so you don't know what continued fractions are, they are a way of representing numbers, such as the number 2014 over 786,543, as a big fraction like this. Some number, an integer, plus 1 over some number, plus 1 over some number, plus 1 over some number, etc. And so there you are. The neat thing, though, is not only can you represent rational numbers this way, but if you allow them to be infinite, then you can represent any real number this way, in a unique way, except up to this 1, 1 versus 2 thing, in an almost unique way. Let me show you a few more examples, and then we'll start proving things about these. Now it's kind of boring. Here's the continued fraction of pi. Notice that this just stops after a certain point. What happens is that if you give it a number that's sort of an abstract number, like pi, it's some transcendental number, what it'll do is it just takes, and by default it'll just take 53 bits of precision, that is double precision, and what it does is it applies a certain procedure, which I haven't told you about yet, that gives back a continued fraction. It basically step-by-step computes numbers like this using an algorithm that I haven't told you about, such that if you were to write out this whole continued fraction, you end up getting something that's very close to that number right there. You can increase the number of bits of precision and you get a longer continued fraction expansion, as you can see here. So let's just try this in a little more detail with pi. So here's the continued fraction of pi. There's a command, so if you do c.tab, you'll see that there's lots of methods or things you can do with a continued fraction. One of them is you can call the convergence method. And what that will give you is, it's the following. So if we were to type show of c, you see this big massive fraction, right? What convergence does is it just forgets about everything after some point and simplifies the result. Of course, internally what it does is it computes the Pn and Qn using the recurrence. So the first conversion is just 3. Then next, if you forget about everything after the 7, it's 3 plus 1 over 7. And that's 22 sevenths, which is another famous approximation for pi. If you then forget everything after the 15, you'll get another approximation for pi, and that's the number right here under convergence, 333 over 106. So that's right there. If you forget everything after the whatever the next one was, then you get this convergent, etc. So these are better and better approximations for pi. That's what these convergents are. Actually, just for fun, let's look at what they are in decimal. So print out the rational number, and then I'll print out its decimal expansion to, say, 300 bits of precision. That's kind of ugly. How about if I go to, say, 50 bits of precision? That's not so good. 100 bits. Okay. So the first convergence 3.0, 22 sevenths, 3.14, 333 over 106, 3.1415, 355 over 113, 3.141592. 92. And then 103,998, etc. So see, each one's getting to be, is closer and closer to pi. One of the things we're going to prove today, by the way, we will prove that the sequence of numbers given by some procedure I haven't told you yet, we'll prove that the difference between pi and this number is less than the square of the denominator right here. So we'll give a very precise bound on how good each one of these approximations are. We'll prove that completely. Okay? Here's a little interact, by the way, that just, you give it a number like pi and it gives you back and a certain number of bits and it gives you back the convergence and the continued fraction. So you can put e in here. So there's the continued fraction of e, which has a very nice pattern. And by the way, e squared also has a nice pattern. I guess you can't see it here, but I claim it has a nice pattern. Pretty hard to see. E squared has a nice pattern, trust me. Well, how about this? If we do continued fraction of e, and I'll just say bits equals 300. Oh, e is fine, but what about e squared? Does anybody see a pattern in this?
113, 6, 9.
Yeah, there's a pattern. Look. So there's a pattern there.
18, 30, 42 is plus into 12.
There's a pattern. And in all the powers of e, there's a pattern. But as far as we know, there's no pattern whatsoever in the continued fraction of pi. Fibonacci numbers are related to continued fractions. So I mentioned that before, but if you define the Fibonacci numbers as given, so the nth term is the sum of the previous two, then here's the first few Fibonacci numbers. Here's the continued fraction of 1 plus root 5 over 2, but now look at the convergence of this continued fraction. So if you do convergence of the continued fraction of pi, of 1 plus root 5 over 2, these numbers, the numerators, are exactly the Fibonacci numbers. Okay, let me show you. Okay, so I'm just going to give you a hint of some other amazing things that are coming up. So first, we're going to prove a theorem, not today, but next week, that if you consider a continued fraction that goes on forever and repeats, so it's not like just that there's a pattern, but it's a repeating pattern. It's exactly the same thing over and over again. Like here where you see 1, 1, 1, 4, 1, 1, 1, 4, going on indefinitely. That happens if and only if your number is a quadratic irrational, meaning it's something that you can express in terms of a square root. It's a root of a quadratic polynomial. That's not actually a rational number. Okay? We're going to prove if and only if there. So it's pretty amazing. But that somehow, remember with normal decimals, a decimal starts repeating if and only if the number is what kind of number? Like 1.33333. If it goes 3 forever, what sort of number will you get for sure? A rational number, right? Rational numbers are exactly the decimals that repeat forever. They have a repeating pattern. With continued fractions, the numbers that the real numbers whose continued fraction repeats forever are exactly the roots of a quadratic polynomial. So it's kind of like a deeper, you get a kind of a deeper perspective on the real numbers by introducing this idea of continued fractions. And now let me tell you an unsolved problem. If you take a number like the cube root of 2, take that real number, or any root of any polynomial of degree greater than 2 that's irreducible, and consider its continued fraction, There's a unique way of getting a continued fraction associated to a number. That's weird, I turned my phone off. Okay, so how is that even possible? Okay, so here's the open problem. You have a bunch of numbers here. Is it bounded or unbounded as you extend the sequence indefinitely? Nobody knows. It could be that there's some absolute bound on the size of the numbers that come out of this procedure, which I haven't told you about yet, or maybe they're uniformly bounded. They're all less than 1,000. So you can try a larger number of bits, you get more numbers out, you get a better continued fraction expansion. Does anything bigger than 600 ever appear here? I mean, if you compute long enough, probably you'll see something. There's a lot of things you could try to do involving maybe computing. You could draw a frequency histogram and see if there's some model for the numbers that are coming out. Try to make a guess as to whether or not these are unbounded or bounded or how they behave. People have done a lot of calculations like that, but nobody can prove anything. So without further ado, I should now stop with the showing you lots of random stuff with the computer. And now I'll quickly remind you of the theorems we proved last time, and then I'll tell you how, given any real number, there's a very simple procedure that spits out a continued fraction that converges to that real number. Okay? Also, there was a question that somebody asked right when I was coming into the classroom today, which was, if you have a continued fraction already, like it has an expansion like 3, 8, something like that, and you just want to work with it, it can't be 0. What do? Well, you can just do this, continued underscore fraction, just like that, and then you can work with it. Okay, so we just say continued underscore fraction, and you give the list of numbers a sub I as a list. All right, so that's done.